Welcome to week 11. I can't believe we are in week 11 already. And today we are going to discuss center of gravity, centroids, and centroids by integration and composite bodies. So, very interesting topic. We have been talking about forces and moments. We introduced friction. We did 3D. We solved for reactions. We got shear force diagrams, bending moment diagrams. And sometimes we have accounted for the self weight of some in some of the examples, right? But in reality, all bodies have weight, right? And then being able to identify where does that weight appears to be concentrated in the body, so we can replace it by a resultant force. And why would we do that? Well, just to make it easy on us when we are calculating reactions, right? Easier to deal with a single force that passes through that apparent center of mass or weight in the body than just having all the particles that make up the body having its own weight, right? There'll be hundreds of them if we want to make our or to do our problem realistically, right? But better to replace that by a resultant force, and then we can really simplify our calculations. So that's the actual motivation of this topic, and we'll be discussing center of gravity in this first section. So center of gravity, we have mostly so far ignored the effects of self-weight on rigid bodies, and when we have considered it, the rigid bodies have been simple shapes, circles, triangles, and rectangles, in which the self-weight acts at the center or the apparent center of the body. So, but that's not what happens in realistic problems, right? In day-to-day engineering problems, the geometry of the items we design is usually more complex than a rectangle or a circle. Now, to complicate matters, part made of several could be, right, made of several materials, and they may have variable density. So you have a square, right, square shape on your beam, for example, but right, it's made of two materials. It's made of two materials, and this material is heavier than the material to the left, right? So where is the center of mass of such a body, right? Closer to the lighter side, closer to the heavier side? Well, that's a sort of question we want to, or we are aiming to answer, right? So the center of gravity, right? Now, to solve for the forces and or reactions in a system, what we have been doing, we need to be able to calculate basic quantities of, such as the magnitude of the self-weight, right, and its location in the body, right? And in addition, right, what are the reactive restraints, right, the reactions, and what are the applied forces, right? So, but regarding to the rigid body, that's what we are interested in, right? The magnitude of the self-weight and its location. Now, if the body is symmetrical and it's made of uniform material, so the same material everywhere, the center of gravity is located at the geometric center of the body. For example, for a square, right, for a squared shape, this the place where the weight appears to be concentrated and passes is just at the centroid. For a circle, right, for a circle, in the same way, right, at the center, right at the center of the shape, right. Now, this geometric center, another word for it, is the centroid, right? We are going to discuss it later. Now, this one is this concept. Let's say you take a piece of paper, right, and you cut that piece of paper in an arbitrary way, right? So it used to be rectangular, and then you cut some pieces off, right, arbitrarily. You cut some pieces off like this. And then you remain only with the white part. Now, with your finger, you want to be able to balance that piece of paper with your finger. And the question is, right, where do you place your finger so you equilibrate that piece of paper completely? Well, you have to equilibrate it in what we call the centroid, right? This is the centroid of the shape. Well, if that shape, right, we account for the weight of the piece of paper, right, if it's made of paper and just paper, right, the location of the center of gravity is the same as the position of the centroid, right? This, of course, the assumption is that this shape is made of the same material. Now, in reality, bodies are not symmetrical, right? That's the reality. Bodies are not symmetrical in general, and they are not made from uniform materials, right? So we need to calculate where the center of gravity is located. This is the subject of this set of lectures. Now, consider the system that we are showing in this figure, and this system is made up by 3 particles. And these 3 particles, as evidenced by their apparent sizes, right? They may have made of different masses, right? So all of them are pulled towards the Earth with different forces, right? So because of the mass, right? The weight, of course, is mass times the gravity. So they have different masses, so they have different weights, right? So this rigid body is made up by these 3 particles, right? These 3 particles. They are, of course, they don't move relative to each other, right? They are just, for example, we can see that particle 3 has a very large weight, right? And then for this particular case, let's see what happens, right? Let's see what happens. In this case, right, the assumption is that we have gravity. The gravity is acting along the x-axis, pulling all these particles down. And the question is, where is the center of gravity, right? Where is the center of gravity? What is the 3D coordinate? Since we have a 3D system, what is a 3D coordinate in which we can pass a resultant force, right? A resultant force and have the same effect as having 3 particles spread out, right, or scattered. There should be one specific point on this body in which we can pass that resultant force, right? And the point lives in 3D, right? It's just there are these 3D coordinates, 3 coordinates of this point, and the idea is that if we can locate it and if we pass the resultant force through it, we should have the same effects, right? So let's see what happens. So earlier, right, in our course, we saw that we could define equivalent forces, and equivalent forces are easy to get, right? It's just the sum, just the addition of all the forces, and this is just following the idea that is the sum of forces in a certain direction. So getting that resultant force is not a problem, right? Because that resultant force, Fr, is just the sum of all the forces in this particle. So in this particular situation, all these forces act down in Z, right? So Fr is just the sum of W1 plus W2 plus W3. Getting the magnitude of Fr is not a problem. Getting the position of Fr, that could be a challenge, right? Now, it's the same problem as before, right? We have to preserve that rotational tendency. The resultant force has to have the same rotational effect. So the moment caused by Fr has to be the same as the moment caused by the three particles, right? So the equivalent couple, right, is based on the turning effects caused by the original set of forces, and the resultant force has to have the same turning effect, right? Now, rather than substitute or replace that system of 3 forces with a force and a couple, right? Let's just place the force with the right moment arm, right? With the right moment arm, and that will allow us to obtain the position of that equivalent point. The point is, the original moment, right? The original moment caused by the 3 particles has to be equal to the moment caused by the resultant force, right? So we have to choose axis of reference to find that, right? We have to locate all these particles in the moment arms so we can start working. And again, right, we have done this problem before, right? We did it for 2D when we found the position of the resultant force, right? So now it's 3D. We just have to do it 3 times to find the three coordinates. So here's the moment arm of with respect to the xz plane. So these are the y moment arms, or the moment arms in y. And then for each particle we have a moment arm, right? For each particle we have a moment arm. And we have the resultant force, right? That is the resultant force equal to the 3 weights. And then we have that that resultant force with a moment arm, which we don't know yet, right? We call it y bar, right? Y bar, the one in red. And the challenge is to find it or to calculate it, right? We are helped by the fact that we can establish the same equation for moments. So here are the moments of the 3 particles, right? The moments of the 3 particles, and this is the moment of the resultant force. So we can solve for y bar in this equation, and then we have this equation, and then in a kind of a schematic way, right, we can have the position of y bar equal to the sum of all the products of y bar times the weight of each particle divided by the sum of all the weights of all the particles. And in the same way we can do that, right, for the position of the y bar coordinate and the position of the z bar coordinate, right? So the formulas are quite similar, right? And they are very similar to the ones that we were using when we defined the axis in 2D. Now, the direction of the gravity, it didn't matter. The direction that these particles are being pulled, right, it won't matter. If we have the gravity acting on the z-axis or the x-axis or along the y-axis, the 3 particles, right, the position of the x bar, y bar, and z bar, the position of the resultant force won't change, right? We'll just have the resultant force just passing through the same point and being pulled by whatever direction the gravity is acting in, right? So it's independent of the position of the gravity force. Now, as a summary, we have the 3 formulas, right? Knowing the weight of the particles, right, we can do a discrete approximation, right, and then find the position of the coordinates of the center of gravity, right? Now, there is another very related, and then of course, right, this is independent of the direction of the gravity, right? In these expressions, the expressions above, right, there is no, we didn't actually, the direction of the gravity didn't actually play a role, right? So in these coordinates, x bar, y bar, and z bar, they are independent from the direction or the assumed direction of the gravity. Now, a related concept is the center of mass, right? We just dealt with the center of weight. Center of mass, if you are located in the Earth, right, the gravity is pretty much uniform among all bodies. So the center of gravity will be equal to the center of mass, right? Because right, weight is equal to mass times the gravity. If the gravity is the same with all the particles in your rigid body, right? Right, it doesn't matter what the gravity is, right? Once we do the, let me just go back one slide. Right? If I replace this weight by mass of the object times the gravity of the object, I have to do it, right? All these times the z coordinate. If I divide by mig, right? These g's here cancel each other out, right? So the same equations can be used when I am looking for the center of mass, defined as the apparent point in which all the mass appears to be located, right? Now, since in a typical rigid body, right, all these particles will be subjected to the same gravity. The equations to get the center of mass are very similar to the equations used to calculate the center of gravity, right? We just replace the weight by the mass, right? And we have very similar expressions. Now, it's a time to to solve an example, right? And I have 3 particles, and then the question is to find the center of gravity for these 3 particles. Now, as a heads up, we are looking for a point in 3D, right? We are looking for the center of gravity will be will have 3 coordinates, right? X bar, Y bar, and Z bar. And then I have the weights of each particle, right? You see, 10 newtons, 20 newtons, 10 newtons. And I have the coordinates because in this 3D Cartesian plane, I have some measurements that I can use to find the coordinates. So it seems like I have everything to apply the equation from the previous slides. So here is my drawing, right? And here is us calculating the coordinates, and then these are the coordinates for each point, right? It's just a matter of applying the formulas. So for example, right, this is the resultant force, right? This is the sum of all the weights. 10 plus 20 plus 10 gives me 40 newtons, right? And then let's find x bar, and x bar is just, right, the old moment equal to the new moment. We can solve for x bar, right? The sum of all the positions of the particles in x times the weight of the particles divided by the sum of all the weights. And then when we evaluate, right, position of each particle is the x position. So I have 0, minus 2, and 4. So 0, minus 2, and 4 times the weight of each particle, 10, 20, and 10, right? 10, 20, and 10 divided by 10 plus 20 plus 10, that's the weight of each particle. And I get x bar equal to 0. So the coordinate of the first coordinate of the center of gravity is going to be 0. And in the same way, I apply the same formulas for the y bar component, and I get 1.25. And I do the same for the z component, and then I get it equal to 1. So the center of gravity is located at 0, 1.25, 1 meter, right? That point is the point in which I could replace the, 0, right? Let me just show you 1.25, which is 1.25, and then 1 meter, which is here. So in this point, I can replace the 3 loads by the resultant load, and I will cause the same moments as this rigid body in any direction, right? I can just place WR through that point, and it is the same as having that 3-particle body, right? 3-particle body. And for the purposes of calculations, these will make things quite straightforward, right? Now, the reality is that our bodies are made up by many particles, right? Many small particles, right? If we want to add them all together, right, we found ourselves quickly overwhelmed, as a sum is going to have many terms. It's better to integrate, right? You remember? We have to use calculus because we can use an integral, which is just a sum over a continuous domain, right? And it can actually simplify our calculations, right? So calculus, an integral is just a sum, right? And we can add lots of little tiny areas or volumes or weights to get our resultant force, for example, right? So it's the same thing, right? We use the same formulas, but we don't actually call them sums anymore. We actually call them integrals, right? So we're going to use integration. So let's see how the formulas change. So in calculus form, I have my previous expressions, right? And I have the only difference is, or that we may see, is that now we have differentials of weight, right? Differentials of weight on my equation, right? So from discrete formulas with sums, now I have continuous forms, which are in integrals, right? And then I have the location of a small piece and the weight of the small piece. So that is why it's a differential of weight, right? A differential of weight, dW, right? And we have that for x bar, y bar, and z bar, right? And z bar. And we just have to integrate over the whole body. Now take a look at these integrals. The position of the differential element is one of the straightforward quantities, right? In many cases, the differential of weight merits certain attention because the way that we define it, right? The way that we define this is just the idea, right? This here is just the idea that we have to integrate over the whole body. The way that we define the differential of weight, right, can simplify our life a lot, right? And it can also allow us to include a variation in density, right? Cases in which materials are made up by 2 or more materials, or one material is more dense towards one side than the other, right? And we are going to achieve that by defining dW in a convenient way. Now, this paragraph, as we said, is just talking about the fact that that we have to integrate over the whole body, right? For this integral to be valid. So differential of weight, right? Differential of weight. Let's make use of one very handy definition that will simplify our life. We need to define it, right? Define the differential weight element given by dW, right? And if we introduce the idea of specific weight gamma is defined as weight over volume, right? Weight over volume. And then the units of the specific weight are just Newton over cubic meter, right? Specific weight. And we can define then we can define the weight in terms of a specific weight. And you may be wondering, what's the point of defining specific weight? Well, because specific weight is a property that sometimes you'll have, right? When told that your body is made up by or has different densities, right? You will be told that in terms of specific weight, right? Things will be heavier towards that side, right? That means that they have higher specific weight towards that side, right? Heavier, more specific weight. So, right, we can express weight following this formula here. We can express weight in terms of specific weight as this, right? Weight equal to gamma times volume, right? Specific weight times volume. And then if we apply the differential definition, is just right, the differential of weight equal to specific weight times the differential of volume, right? If we derive both sides of this equation, we obtain this other equation. Now, the volume, right? The differential of volume depends on geometry, right? So we can calculate the differential of weight, right, through a differential of volume, right, which presumably will be easier to get, right? So it's easier to work with volumes because we can set up integrals to deal with them in an easier way than we could set up our integrals with weight. So we can rewrite our previous equations, right? We can rewrite our previous equations in which we have differential of weight. We can express those as equivalent expressions using now specific weight and volume, right? Using this definition that we have over here. Yeah, many problems you will be given the variation of the weight via gamma, and then you just have to play with volumes, right? With volumes. So this is for weight. We can do the same for mass, right? We can do the same, or you apply the same definition for mass, right? In this case, we have previously defined specific weight, right? Specific weight, and then for mass, it's convenient to define density, right? Or to express things in terms of density. Density is mass per unit volume, right? So it is kilograms, the units per cubic meter, right? And then density is just, according to the definition, is just mass over volume, right? And if you remember that specific weight was weight over volume, and weight is mass times gravity over volume, right? We can define specific weight as density times gravity, right? So this will come very handy since gravity is a constant for the problems that we will be dealing with, right? We can easily express specific weight using density, right? Coming from, if you're given density, you can express specific weight by dividing by g, or if you are given, if you are given density, right, you can express specific weight just by multiplying gravity, and using this equation, right, you can then deal with all cases. So center of mass can be expressed in this way, right, or expressed in this way, just making use of the specific weight relationships or the density expression, right? And it'll be just a matter of knowing what equation to use, right? What equation to use. So I have this example here, right? Example 2, and this example deals with the center of, I think it's the center of mass, center of gravity, right? Center of gravity. Center of gravity for this drum, right, is a cylinder. The specific weight, right, varies directly with its distance from the base, such that gamma is equal to 200 times the z coordinate in pounds per cubic foot, right? And the height of the cylinder is 4 feet. What this means, right? What this means is that this cylinder, right, becomes more dense, weighs more the farther we go from the base. So, right, this cylinder is heavier on the top, right? It's heavier on the top. Take a look at how it's located in the x and y axis, in x, y, and z axis. So we expect the center of gravity to be located on the z axis, right, along the z axis. So 0, 0, 0, z, right? We are looking for that z bar point that determines the center of gravity of this object, right? Because of symmetry, we know that it's at x equal to 0 and y equal to 0, and it just rises on z. Now, if the heavier part is in the top, right? This is heavier, and this is lighter. Where do you feel the center of gravity is, right? Closer to the base or closer to the top? Well, if it becomes heavier towards the top, right, the center of gravity should be closer, right? Should be closer to the top, right? That's what we envision. If the height is 4 feet, maybe, right, maybe z bar is closer to 3, right? Who knows? It's more than 2, right? It's more than 2. So a quick check will be that whatever value we get shall be bigger than 2. So in this slide we have our drawing, and I think the first step, and you would agree with me, is that we need to find the right formula. Now we saw many, right? Center of mass, center of gravity, and then we have now a few more based on specific weight and density, and we have to find the right formula, right? So it can help us the most. We need a formula for the center of mass that involves the specific weight and volume, right? These are the things that we need. So I have these equations for you, right, for your consideration. I have equations that will allow us to get our x bar, y bar, and z bar coordinates. Indeed, these two guys are 0, right? X and y, right? So this guy is 0 and this guy is 0, right? You will be in agreement with me that z bar, right, we just need the equation for the specific weight, which is given here, right? Gamma equal to 200 times z in terms of pounds per cubic foot. And then we need a differential of volume, right? Differential of volume, which you may or may not remember from your calculus courses. But a differential of volume is just the piece that we are going to add, right, with the integral, right? So obviously we have to integrate along z, right, along the z-axis. So it's good, right? It's good if we define our differential element as a disk, right? As a disk. So we have a disk here, and the differential of volume of this disk, of course, is the area of the disk, which is P times R squared. Right? That's the area of the disk times the height of the disk. And the height of the disk is the differential of z, because we are integrating along that direction. So this is the height. And together, right, they give us our differential of volume, right? Our differential of volume, that this is the differential of volume. Very often the most difficult part of one of these problems is actually setting up the integral, right? The integrals themselves are quite nice in terms that we'll just have polynomials to solve, but setting up the integral is where most of the work will be required. Now you'll be seeing in these formulas, right? You'll be seeing quite a bit of this x squiggle, right? If you have this, let's say, I'm talking about these things. So x squiggle, this is not the same as x bar, right? It's not the same. Now, x squiggle, y squiggle, and z squiggle are the coordinates of the centroid, the coordinates of the centroid of the differential element, right? The coordinates of the centroid of the differential element. Now, x squiggle for this case is 0. Y squiggle in this case is equal to 0. And z squiggle, right, is equal to the very same variable of integration z, right? Z is equal to z squiggle, right? So in this case, z squiggle is equal to z. And then in the equations above, right, we can replace z squiggle by just the variable of integration z. So we don't have to worry about, yeah, how do we integrate z squiggle? Well, z squiggle is just equal to z in this particular case, right? So I have this is the equation I need, right? That's the equation I need. And I can see that we can do it. We can find z bar by just integrating the numerator and the denominator as two integrals, so a and b. You can divide that that fraction into two, and then we just divide a over b, right? Whatever you get. So note, right? Z bar is the distance to the centroid, the distance of the centroid, the distance to the center of gravity of the entire shape, and Z bar is the distance to the centroid of the little disk, right? Don't forget, right? We're looking for this guy, and this is just the Z squiggle is the distance to the centroid of the little disk, right? So just as a reminder. In these equations, remember our gamma, right? Our value of gamma is equal to 200 times the 200 times Z. And let's start with our integration. The volume of the differential of volume, right, as we saw it before, is area times the height. So this is the area, right? This is the area, and this is the thickness, right? The height, right? Dz. So this is our differential of volume, right? R is a constant. You see the radius of this cylinder is a constant in itself, so it's going to remain a constant. And then dz is a variable, right? It's a variable. So let's p is also a constant, right? And I say p as the Greek would call p, right? I know that you also would call it pi, right? But I tend to pronounce it as the Greek would actually do it. But sometimes I say pi, sometimes I say p, right? I like to call it p. Okay, it's constant as well. What else? Well, we can write now my integral a. So what about we rewrite our integral a equal to z squiggle times gamma times dv, which can be written as, right? Can be rewritten as if z is the height of the disk centroid, right? And z is also the distance of the disk from the origin. In this particular case, z squiggle is equal to z. So the first change in the integral is z by z squiggle. Gamma, specific weight, is 200 times z. And then dv is p times r squared times dz. So the variable we want to keep inside the integral is z and dz, right? And all the constants can actually go outside of my integral, right? So I write my integral as right, 200 times p times r squared, all my constants, and I just leave inside z squared times dz. And you know that the integral of this guy, right, is just z cubed divided by 3. And now I have just to integrate, right, or to to evaluate the integral from 0 to 4, right, from 0 to 4 feet. So my integral, I have to evaluate it, right, from 0 to 4. From 0 to 4, which means to evaluate first for 4, then minus that for 0. And then we'll obtain 4,267 times P times R squared pounds per feet, right? So this is the value of the integral on the numerator of my expression, right? So this guy over here. And now I'm ready to evaluate the denominator, right? Integral of gamma times dv. Okay, so gamma times dv, right? This integral, right? I can substitute, just replace gamma, and then dv, right? It's much nicer integral because my integral is just z times dz, which I integrate, right? Remember, this is z squared divided by 2. I integrate from 0 to 4, and I get it equal to 1600 p times r squared pounds. Now, if I divide a over b, right, I divide the previous value a by b, right, and I obtain that the center of gravity is 2.67 feet. I was expecting it to be bigger than 2, so it actually corresponds quite well with what we were expecting. So in this problem, I just want you to not to worry about, because it seems complex. I'm aware it seems complex. It's the first time we apply one of these formulas, and it was tricky, right? How did I know that it was a disk, the one that I had to integrate, right? Well, it won't always be a disk, right? Depends on the shape. So just at this point, try to be just very careful in understanding the big picture, right? We have equations to calculate center of gravity, center of mass, which happen to be the same for common objects placed on Earth, right, at the same level, and in rigid bodies acted by the same gravity. So you have equations. Make sure you know how to set up your integrals with specific weight, with density, right? Sometimes a trial and error process will be needed until you get the same variable of integration on your integral, right? You have to have only one, right? Cannot integrate more than 2 variables, right? Not at this point, right? There is multivariable calculus, but at this point you need to have only one variable. So make all the conversions, be creative, use the geometry of the shape, use whatever relationship between the variables you see, so as to efficiently set up your integrals, right? After you set up the integral, it's just calculus. You can feed it to your calculator and obtain a solution, right? These problems, the physics doesn't require, I am not going to require you to be experts in calculus, but setting up the integrals, that's key, right? In the next video, we'll be talking about centroids, right? Centroids. And this is just a point in a body that in which all this mass is located, right? And how do we obtain that point based on simple geometry, right? So it could be the center of a volume, right, or the center of a plane shape, 2D shape, or even the center of a line, right? So we'll be playing with the calculus formulation for this. Well, see you, and thank you, and see you on the next video.